Okay, so when light reflects from the surface of a plane mirror, the angle of incidence is equal to the angle of reflection. Easy one. So the diagram shows light coming from an object. If it says continue the two rays, I'm going to have to do this freehand, unfortunately, because it's very difficult to draw on the screen with a ruler. But obviously you should do this with a pencil and with a ruler. Okay, so we've continued the two rays, and then above we just stated the law of reflection, which is this angle here is going to be equal to this angle here. Now you don't have to draw that with a protractor, but obviously if you measured it exactly with a protractor to make sure that I was the same as R, then that would give you a greater chance of getting the marks for the question. And same thing here, but it certainly has to be by eye that these two angles are about the same. If you've done it right, then these two rays here should be diverging from each other, which means that they're not quite parallel, they're moving away from each other. All of that gets you 1 mark so far, and then we've got to show how an image is formed. Okay, so our eyes, if we're the observer standing here, our eyes and our brain is very used to light travelling in a straight line, so that's what we imagine. Our brain imagines happens. So if you continue these lines back, and this line back here, okay, then you'll see that they cross at a point about here, and that's obviously the image. And if you've done it all carefully, then that distance there and that distance there, those two distances are going to be equal to each other. So the second mark for constructing these lines that go back to the image behind the mirror. Final part to this question is, how can you tell that it's a virtual image? Well, if you look, then the rays don't actually converge on the image. These dotted lines here show that that's not actually where the light's going. The light rays actually converge on the object. So the idea is that the image is behind the mirror, or appears to be behind the mirror, if you like. It's virtual because it's not real. You can't reach around the mirror and actually touch that. Okay, next question is about total internal reflection. So let's complete the diagram to show the path of light as it enters and passes through the optical fibre. Now, if we're doing this properly, which of course we'd like to do, then we'll notice that this angle here, because it's going from air, which has got a low optical density, to glass, which has got a high optical density, then you guys might remember LHT, which means that it's going to get bent, the ray is going to get bent towards the normal, so this angle here is going to be smaller than this angle here. Okay, the angle of incidence is going to be greater than the angle of refraction there. They don't actually give you a mark for that in the mark scheme, okay, but it's just good physics, and I have seen some mark schemes where they do award a mark for that, so do that one carefully. Okay, now it's total internal reflection, which means all of the ray gets reflected, and just I equals R, as we've already said, so the angle of incidence is equal to the angle of reflection. If you draw a normal perpendicular to the boundary, I always find that helps. Okay, and there we go. So you get 1 mark if you've done the first of these, and then to get the second mark you need 3 or more of these reflections going on, and you can see for each one of these I've got to get the angle of incidence approximately the same as the angle of reflection. And to finish it off, because it's a ray diagram, of course it should have arrows showing the direction of the rays as well. Okay, so 2 conditions required for total internal reflection to happen. The textbook one that they're after here is that this angle here, which I'm going to call I, that I, the angle of incidence, has got to be greater than C, where C is the critical angle. The second one takes a little bit more thinking about, because it's total internal reflection. Total internal reflection only works where you've got a boundary, for example here, where you've got high optical density going from high optical density to low optical density. It's bouncing off the inside surface there. So the second condition is that the boundary of the high optical density to low optical density. Or the other way that you could say that is if you talked about the refractive index of the two things, there's N1 and there's N2, then N1, the refractive index, would be greater than N2. So a couple of different ways that you could get that second point there. Okay, an advantage of using optical fibres is that when light travels down an optical fibre, the optical fibre does not get hot, it doesn't get heated. Maybe get hot, yeah, does not get hot. The obvious one that I was thinking of was that copper is actually very expensive, whereas optical fibres are basically made out of glass. Glass is made from melted sand, and sand is a very silicon dioxide is a particularly cheap substance. You can get it for free at your nearest beach. But unfortunately in the marks game it said ignore any references to that. It also said ignore references to the speed as well, but that makes sense because a signal can travel along an electric wire at the speed of light, and then the light will travel at an optical fibre at the speed of light as well. So there's no difference in terms of their speeds.